This is the video for Math 120, section 2.5. This section is covering infinite limits. So the first example question that they give you here is the limit of a polynomial over a polynomial, which is a rational function. So when you have a rational function, you can basically get rid of everything except the highest powers. So the limit here should be 3/4. Now algebraically, the solution that they're sending you through is helping you to discover what the limit is by doing algebraic steps. So if I divide by the highest power in both the numerator and the denominator, I end up with x squared being distributed to each one of the terms here. So we want the limit of this, and our limit rule says that the limits, if we add a bunch of stuff together and they're nice, the limit's going to be the same, and all of these have nice limits. The limit as x goes to infinity of 1 over x is one of the ones you need to write down and remember, because that one is 0. So this limit is 0. The limit of 1 over x squared, of course, is then 0 too. So the limit as x goes to infinity of 1 over x is 0. So if we can examine that on our calculator, go to y equals, we're going to put in 1 divided by x. And I'll do a zoom 6. You can see as this function goes to, as x goes to infinity, it gets smaller and smaller out as x gets larger and larger. So 1 over x, 1 over 10 would be 1/10, 1 over 100 would be 1/100th. So this is going to 0. It's hugging the x-axis, and that's the same as having a horizontal asymptote of y equals 0. So y equals 0 is the x-axis. So that's basically what it's saying. I could have told what the limit was right here, because everything goes away except for the highest powers in the numerator and the denominator. Then I reduce, I get 3/4, and that's the same as y is equal to 3/4 as the horizontal asymptote. So looking at another graph, we could have different horizontal asymptotes, and it's okay if we cross them with our graphs. We can't cross vertical ones, but with our horizontal asymptotes we can. So the horizontal asymptote is really describing end behavior. So we're saying what's going to happen at the ends of these. So this function looks like it's settling up to -1. So if it looks like it's hugging a particular line, that would be the horizontal asymptote. So the limit as x goes to infinity here is -1. Going to negative infinity, it's hugging up to the line y equals 2. So y equals 2 is the horizontal asymptote. And as the limit goes to negative infinity, as x goes to negative infinity, to the f of x value goes to 2. The y value goes to 2. So there are horizontal asymptotes here, y equals 2, y equals -1. We find those by finding the limits at both infinity and negative infinity. So having rational expressions and having infinity and 0, those are strange spots on a graph. Usually something equals to 0 or you're going to infinity. We have 7 indeterminate forms, and I'll ask you what are the indeterminate forms on the test. 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity, 1 to the infinity, and I usually start by putting a 1 here, 1 to the infinity, infinity to the 0, 0 to the 0. So there's 2 infinities in here and there are 3 zeros at the end. Someone a few years ago said this looks like Mickey Mouse ears at the end, and that helped them to remember infinity to the 0, 0 to the 0. Now, the limit as x goes to infinity of 1 over x, we just talked about that, looked at the calculator for a second, and said that both of those limits are 0. So those are important to know. This one equals 0, and this one equals 0. Now, the theorem says that if you're finding the limit of rational expressions, you can just get rid of everything except the highest powers. So you can get rid of these. The limits are the same. It does not say the functions are still the same. It says the limits will be the same as we go to infinity. So infinity is important. So we have, if we reduce this, we end up with 3/5. So our limit is 3/5. For the next one, the limit as x goes to infinity of x squared. Our highest powers here as the x squared and the negative x. And be careful that you're catching those. So those are going away. So I'll write this is equal to the limit of, as x goes to infinity, of x squared over negative x. Now if I reduce this, I'll have 1x gone. So this will be the limit as x goes to infinity. Now you have to keep writing the limit until you actually take the limit. And I haven't taken it yet. So up here when I said x goes to infinity, there were no x to put in this, so that means the limit was 3/5. But here I still have x's, and when I reduce this, I end up with a negative x. So now I can put the infinity in, and I get negative infinity is my best answer for this limit. This one is an example for infinity minus infinity. So if I put infinity in right now, it's infinity minus infinity, so it's indeterminate. So I have to do some kind of trick. One of the tricks is to factor. Here, if I factor this out, it becomes x times x minus 1. And when it's x times x minus 1 here, then I can put in infinity, and infinity minus 1 is still infinity, so infinity times infinity is infinity. So this becomes arbitrarily large. X squared actually is much bigger than minus x. So algebraically is using the highest power in the denominator, and I think I said numerator or denominator earlier, so make sure you fix that. The highest power in the denominator in this case is x. The highest power of x is x. So I'll divide each term by x. This is doing this algebraically, which is kind of like a proof. And then the limit as x goes to infinity here would be infinity plus 1, which is infinity. And 3 over x would be 0 and then be negative 1. So infinity divided by negative 1 gives me negative infinity. So for this kind of function, it might be easier to look at the calculator. So you can always do these in a calculator, but not all of them are easiest done in the calculator. So let's do f of x equals 1 minus 2 to the x, all over x. So that's 1 minus 2 over x, rather, 2 over x to the x power. Now if I look at the graph of this, do a zoom 6 and see what the graph looks like. I'm interested in the end behavior. So it's looking like at the ends it's actually going to 0. So let's see if that's true. I'm doing second table set, and I want to set it at a large number, maybe 1,000,000. 1, 2, 3, 4, 5, 6. And then instead of making really smalls, I'm going to jump across really large. So 1,000,000 again. So my delta table is 1,000,000 apart. So when I look at my x values, I see that my x values are 1 times 10 to the 6, which is 1,000,000, all the way up. And this isn't changing. So this is looking like as x goes to infinity, it's looking like the answer is 0.1353. If I look towards negative infinity, so let me go back to my table set and set it up at 1,000,000, negative 1,000,000 rather, negative 1,000,000. This is looking towards negative infinity, so second table. And I can see as I go more and more towards negative infinity, which would be going up on my table, I still get this 0.1353. So this has a horizontal asymptote for y equals 0.1353. And really that should be y equals 0.135 because we go to 3 decimal place unless it says otherwise. So if I quit out of this, I believe this is the function that defines, as x goes to infinity, it defines the number e. So e is a limit, like pi is a limit. You may not have seen the limit of pi before, but e is the limit. If this had a 1 here, plus 1, then it would be e. So if I do second e to the negative 2, I get that 0.1353352832. So this I could write in closed form as 1 over e squared. So this is actually 1 over e squared, which is the same as, well, approximately 0.135. You wouldn't be responsible for the 1 over e squared, but this really is part of the definition of e, so you might be able to recognize that as we go through this method. So before we go back to the exercises from WebAssign, let's actually work through some examples here. So this says the limit as x goes to 1. So this is 1 minus 1. That's going to be squared. So we'll end up with a 0 here. X goes for 1 from either side. It's going to be squared either side. And then 2 minus 1 gives me 1. So this is 1 over 0. So I have to decide whether it's positive or negative infinity. So this I would say is positive infinity. You don't have to put the positive, but I did, just to emphasize the point that I had to choose whether that was positive infinity. Now, if you can't analyze it that way, you're going to need to put it in your calculator and actually look at the graph. So your possible answers for these limits here on this next test will be infinity, negative infinity, does not exist, and this one is not a does not exist, it's an infinity. Actually, it does not exist because it's infinity, but this is the best answer. Or an actual numerical value. So infinity, negative infinity, does not exist, or numerical value. In the next one, if we look at this, if we put -3 in, we get 0 in the denominator. So I'm thinking this. I think I have 0 in the denominator, and I have something else in the numerator, so it's not indeterminate. If it was 0 over 0, it would be. But -3 plus 2 is just going to give me -1. Now, I have to decide whether this is more negative or more positive here. So if I look, put -3 below, that's like -3.1 plus 3 is going to give me negative, so I actually have negative over negative. So my answer should be negative over negative is positive infinity. Because having 0 in the denominator, something else in the numerator, definitely goes to infinity or negative infinity. And you have to decide which one. As x goes to 2 from above here, this would be 2 minus 2, but it's a little bit more, so it would be like it'd be 3 over negative 0.1. So this is definitely going to, so we're thinking this is e to the 3 over 0. Now if this is going positive, this is going to be infinite, but if this is going negative, this will be e to a negative exponent, which makes it go to 0, because the e to the x graph looks like this. So this way it's positive infinity, but over here it's 0. So thinking about the end behavior for e, so like I said, I'm going to put 2 plus, so that's 2.1, so 2 minus 2.1 would give me a negative in the denominator, so this means this is going to e to the negative infinity, and that means negative infinity, so this is 0. Now I'm not expecting you to write what you're thinking here. I'm expecting you to put it in and get it. If you write this, make sure you're like putting in parentheses, this is what I'm thinking. So it's not part of the limit. The limit here equals 0. The limit here equals point infinity, plus infinity, but it's not part of the problem to write this down. It's not part of the answer. To do the cotangent of x, I'd have to know how to put the cotangent in my calculator. So I need to know 3 different formulas for trig. So for my calculator, I need to know that the cosecant of x is 1 over the sine of x. The secant of x, and you'll need to have these memorized, is 1 over the cosine of x. So you'll need these for the rest of the semester. And the cotangent of x is 1 over the tangent of x. Now, just evaluating some of these functions is going to give you weird results because you can't put some values into x for cotangent, but it's okay to put it in for tangent. So when you evaluate, you'll need to look at tables. So let's look at the table around the limit as x goes to pi of the cotangent. So we're going to put in y equals, we want 1 over the tangent. We have sine, cosine, and tangent. Tangent inverse is not the same as the reciprocal of tangent, so you can't use those keys for this problem anyway. So we'll do 1 divided by the tangent of x. So that's how we'd evaluate a cotangent. If I look at the graph, I'm going to do a table set at pi, second pi, and I want it close around pi, so this isn't at infinity, this is close around pi. Our delta table will be small, 0.0001 is what I'll put in. So we'll do a second table. We'll take a look at the values. See, it's huge right here. This is wanting on the negative side, and the negative side is huge, but it's negative. So it's going to negative infinity below pi, and it's going to positive infinity above pi, and they want the negative infinity here. So I can see the numbers here getting larger and larger, and I can see that it'll even a little better if I make my table set, delta table, maybe to the -8. That makes it even smaller. So second table, it's still at it actually, wait a minute, I have to have my second table set at pi, second table. So I got an error there, and I have times 10 to the 8. 1 times 10 to the 8 is a 1 with 8 zeros after it. And this would be negative 1 with 8 zeros after it. So on the left side, to the left, below pi, to the right, to the left of pi, below pi, however you want to say that, you're going to have a negative infinity, and after pi you'd have a positive infinity. For the next problem, if I put 3 in, I get the natural log of 0, which is undefined. But if you know what the natural log function looks like this, then I know that this answer, since 3 positive means I'm going to put like 3.1 squared, this is going to give me just slightly bigger than 0. So I'm looking to the right of 3. Natural log of something bigger than 0, just a little bigger than 0, means I'm going to negative infinity. If you don't see that, then what you'll want to do is the same procedure we just did for the cotangent graph. So either one of those procedures is fine. Depends upon how much you know about these functions, which one you'll actually do. Now for number 20, I'm putting in 2, not infinity, so I can't do my trick. So the emphasis here is we have a couple of things that we're looking at. One is the trick. If I'm going to infinity, these are giving me things that might be infinity. So on your next test, I'll ask you to solve algebraically for some of these, and this is one that I would ask you to solve algebraically for. So I can see the top factors as x times x minus 2, and the bottom factors as x minus 2 times x minus 2. One of these goes away, so I'm left with 2 over 0. So this is actually 2 over 0. That's what I'm thinking. And then I have to put the negative in, so I want something slightly less than 2, which would be like 1.9. That gives me a negative 0 here. Something less than 2 up here is going to give me just still the same 2. So the answer here is negative infinity. For the next one, I'll go to my calculator again. Cosecant is 1 over sine, so I can write this as y equals 1x divided by the sine of x. Or you could write x times 1 over sine x. That would be fine too. So I'm going to do a second table set. I want it at 2 pi, second pi times 2. And I want my delta table small, so I leave it like that. So second table. And I can see this is 6.28 times 10 to the 8. And before, it's probably the same 28 times 10 to the 8. What it looks like it's doing is getting bigger and bigger. This times 10 to the 8 means it's probably going off to infinity. And you can try a smaller delta table and see if that's true. So I have to put this in again, 2 second pi, and then maybe put e to the negative, let's make it 15. So you can try it, make sure. Second table. Now I'm getting errors everywhere. So it's going off to infinity. If you remember, below it, it was negative infinity. But let's go back and check that. So I can get it too far away. Second 2 times pi, second pi, and the negative 15 wasn't very helpful to me, so I'll go back and make that maybe negative 10, see if that works. So you may have to try larger numbers than you're expecting because of the functionality of the calculator, the limitations of the calculator. So here, after 2 pi, so to the right of 2 pi, it looks like it was going to positive infinity. To the left of 2 pi, it looks like it's going to negative infinity. So if I graph this, just do a zoom 6 and graph, or zoom 6 is all you need. And then I put in the value, second calc 2 pi, value of 2 pi. Hit enter. Then it's not giving me anything, but if I do a trace, it'll show me where that 2 pi is. And if I go just a little bit over, you can see some values. So if I do a trace to the left, trace to the right, I can't see it on the graph. It's not all that helpful to me. So you might just stick with the table. But I could see that when I went second calc value at 2 pi, it took me to 2 pi, and if I do a trace, and I want below 2 pi, so that's to the left, I can see this is a negative number, and it's fairly large. So the trace isn't all that helpful to me, but it's not too bad either. You might stick with looking at the table. So we'd write that our value here was negative infinity from the graph. So look in the next view. These are infinite limits, so these are really fast. I can see this says the limit as x goes to infinity, so I can just use the powers that are here. So I'm going to just use these two. The x's go away, so my answer is 3. For x goes to infinity here, I'm just going to use the highest powers. Those are the highest. That's x squared. X to the 0 would be this. So these aren't necessary. If I take the coefficients here, this is 1/2. So I reduce the x cubed, I end up with 1 over 2, that's 1/2. The typical mistake I see is that people put 2 there instead of 1/2. Now as t goes to infinity here, and it doesn't matter negative infinity or infinity, you're going to do the same trick. I'm not using these, I'm just using the highest powers. So if I reduce this, it's the limit as t goes to negative infinity of 1 over t. Now I know 1 over t goes to 0, so there's no sign necessary here, so that's 0. On number 25, I just want the highest power, so I'm really not using any of the numbers here. So this is the same as writing 4u to the 4th over 2u to the 4th, which would give me 2. So you can put more work down if you need to, but you don't always need to put more work down to tell me what the answers are. So for number 26, we have the square root of 9x squared. I can use the same, I'm going to infinity, so I can use that same trick. Highest power in the numerator, highest power in the denominator, but it has a square root. So this is the limit as x goes to infinity of x over the square root of 9x squared would actually be the absolute value of 3x. Because it's always a positive number, the square root's always going to be positive, so I need to put in an absolute value there. So as x goes to infinity, I have a positive over positive, which is going to give me 1/3. For the next one, I actually do something called the conjugate trick. So I multiply by the square root of 9x squared plus x minus 3x over the square root of 9x squared plus x, and this should be plus 3x, sorry. This multiplies to be, I still need the limit because I haven't taken it yet, x goes to infinity of 9x squared plus x minus 9x squared over the square root of 9x squared plus x plus 3x. Now you could have just put this in your calculator to see what this is going to be, but the algebraic steps are here. Sometimes if I ask you to do ones and I haven't said algebraically, if you give me the algebraic steps, I do give you bonus. So here I can see that the numerator, the 9x squares and the 9x squares are going away, so I'm left with the limit as x goes to infinity of x over the square root of 9x squared plus x plus 3x. Now, if I take just the highest powers, this will be the limit as x goes to infinity of x over the absolute value of 3x, because I want the square root of 9x squared, plus 3x. So now these are the same size. So basically all the x's cancel, and I'm left with 1 over 3 plus 3, which gives me 1/6. So if you put that in your calculator, y equals second square root of 9x squared plus x. I'm out of the square root, so then I go to minus 3x. I should have cleared that out before I started, but that's all right. I want to do as x goes to infinity, so if I'm looking at the graph, that's zoom 6, and it looks like an absolute value almost. So we end up with this graph like this. I want the second table set, I want the table start to be at something large. And we want the delta tables to be large because we want an infinite limit. If you want something around a particular value, then you don't want to be large values here. You want an infinite limit. So if I look at my table, I would get 0.1667, 0.17, 0.17, 0.17. Then I get unreasonable results here. It does not say that it's going to infinity here. It's probably that I have my delta table too big. So I'm thinking this is actually my answer, 0.1667, 0.167. So my delta table can actually get the calculator kind of confused. So let me put this as, and see, second table. So we end up with 0.16667. Now, I know that that's 1/6, but let's quit out of here and convince myself. 1 divided by 6 is 0.1667. Or the number that I would expect to see is 0.167, 3 decimal places. So we're going to do the same exercise for the next one. Now there's an A and a B in here. So if you wanted to try this in your calculator, you might make A something like 5 and B something like 11 so that you can figure out what those numbers actually should be for the A and the B. Then you do some fraction, go out and put it in your calculator and do a fraction and see if you could figure out what the actual numbers are. But I'm going to do these by using the conjugate trick. So I'm going to come down here and do this. So I know this, the limit, I'm going to multiply the top and the bottom by the conjugate of this. So I have the square root of x squared plus ax minus the square root of x squared plus bx. So the conjugate is to write them down exactly as they are, change the sign in the middle. You usually do this with square roots. So times the square root of x squared plus ax minus the square root of x squared plus bx. And that should be plus. I did that twice. So we change the signs. So when I multiply the top, I get the limit as x goes to infinity of x squared plus ax minus x squared plus bx in parentheses. And you might put parentheses for both so that you're thinking about it. So this is x squared plus ax square root plus square root of x squared plus bx. Now, the x squares go away because we have x squared minus ax. So then I can see that I have a minus b times x. So let me write it that way. It's the limit as x goes to infinity of a minus b times x. And then if I take the highest powers down here, I have the square root of x squared plus the square root of x squared. Now this is the same as x plus x. We're going to infinity, so this is going to be positive. So this will end up being 2 in the denominator. So this would reduce to 2, or you could write this as 2 of these. So maybe I should do that. This is the limit as x goes to infinity. Sometimes my limits look terrible, but it is LIM as x goes to infinity of a minus b times x over 2 times the square root of x squared, which is the absolute value of x. So my answer ends up being a minus b over 2. Now going back to the web assign problems, these should be a lot easier for you now. The horizontal and vertical asymptote, and I guess I needed to talk about the vertical asymptote for a second. The vertical asymptote is what makes the denominator equal to 0. So we'll work this one on paper. So y equals x squared plus 7. So my horizontal asymptotes, HAs, are the limit as x goes to infinity of y. But my y in this case, it can't be factored. X squared plus 7 doesn't factor. So if I do the limit as x goes to infinity here, you got the limit goes to infinity of x squared, and 9x squared is all I'm going to have to keep because I don't need the rest of these. I just need the highest powers. So this would be 1/9. So I'd write that in my HA, and you have to have an entire equation here. Y is equal to 1/9 is my horizontal asymptote. If you forget the y equals, then you'll lose points there. The vertical asymptote is where the denominator equals 0. So we're going to set the denominator equals 0. 9x squared minus 62x minus 7. So I guess we can see if this factors. We'll have x squared minus 62x minus 63. And I can see that factors pretty easily. So this is x minus 63 times x minus 1. Divide by 9. Divide by 9. And this gives me x minus 7 times, this should be a plus over here, right? Minus 63 plus 1 times 9x plus 1. So my vertical asymptotes are what makes this 0. So x is equal to 7. These are lines, so I need the vertical asymptote as an equation of a line, and it has an x or a y or both in it. And then x is equal to negative 1/9. If I sketch the graph, I can kind of see these features that I just solved for, but they're really hard to see unless you do the algebra. So if you do graph, it looks like there's a horizontal asymptote, a vertical asymptote here, which I said was either at 7, 7's here, or negative 1/9. Now I could check this. Second calc value should give me no value at negative 1 divided by 9. And it gave me no y value there. So it looks like that vertical asymptote is correct. As x goes to infinity here, I could try to see if I can see what that one's going to be, but that's on the table set. So we do second table set. That looks good. Delta table of, and we get second table 0.1111, which is 1/9. So I can check it with a calculator, but when I ask you to do these, I'm expecting the actual values, not decimal accuracy. I'm expecting exact accuracy. Note that on WebAssign for these problems, they already gave you the x equals, and they want you to put the smaller and the larger there. There's a video tutorial example here, but we kind of know how to work these problems already. So you can see what these are going to be from looking at the graph. Number 4 gives you the graph already, so we can see some end behavior here. That's the limits as x goes to infinity and negative infinity. And then there are 2 places where we have vertical asymptotes. And you'll need to talk about what the limits are going to be there. The limit, if it goes in 2 separate places, like a jump here, this is an infinite jump, that limit doesn't exist. So make sure you're putting does not exist when it does not exist. Although the left and right limits here, they want you to put either negative infinity or infinity in. This is basically asking you to look at the table like we have been. You don't have to look at their particular values. Here they want corrected 2 decimal places, and then they want to correct to 4 decimal places. So you're going to make this bigger and bigger as you need to. You noticed from my trick earlier that this is actually going to be e to the negative first power. For these, you can put in the negative 10. You get negative 10 plus 11 gives me a positive 1. Negative 10 minus negative 10 plus 10 would give me 0, of course. So I have some kind of infinity here. I have positive in the numerator. And then negative 10 from below would make it a little bit less, so the negative in the denominator. So you'll have to figure out what the sign is. You put in the number. In the denominator, if it's 0, you're going to have to put something a little smaller to see how it's going to look. Now you could put these on the graph, and you'd be able to tell from the graph. Here, finding the limits of the infinite limit, you can do that trick of just using the highest powers. We're just using the highest powers again. Make sure you're putting an absolute value for the denominator when you take the square root. We already looked at this problem, so we did this one. Here you're going to have infinity or negative infinity, and over here in symbols you can find the infinity symbol. The cosine of x doesn't settle down, so if you look at it, it keeps bouncing back and forth. It never settles down. So it doesn't actually go anywhere, go to a particular place, or go off to infinity. The next one is about what sign it is. Same kind of problem as before with the horizontal and vertical asymptotes. You have to do that conjugate trick to figure this value out, or look in your calculator. They're going to want an exact value, however. For number 17, they're giving you some hints about what the function should be. So if you're going down through this, x goes to positive or negative infinity, that's end behavior, and it's settling down to 0. So I know the numerator and the denominator have to have the same, well actually the denominator has to be a bigger power than the numerator. So all of these have the denominator is a bigger power than the numerator. At x equals 0, f of x goes off to negative infinity. So that means that at 0 it's undefined. So there has to be an x in the denominator. F of 4 equals 0 says that when I put 4 in, that I end up with 0. So if I put 4 here, I end up with infinity. So it can't be 1 with the 4 in the denominator, x minus 4 in the denominator. So there's my hints for that one. You can go through the rest of them there. 18 I already talked about, numerators versus denominators. Number 19, this says t approaches infinity, so this would be e to the negative infinity, and we already looked at that. E to the negative infinity goes to 0, so you should be able to see what the answer here should be. As v goes to c, we end up with v squared over v squared, basically c squared over c squared, so the denominator here is going to be 0. So there's my hint there. There's two answers here that it certainly can't be. Determine whether it's false. Can a function have two different horizontal asymptotes? We've seen graphs that kind of depict what the answer there should be. For my last problem, think about what we said with the cosines.